So welcome back. I think it's the last session for today. Then we have lunch, and then we have these owner meetings if you want to participate in the last thing. And with this, it's actually some background to what we saw in the beginning of today with the CP2K. But what I didn't mention there was about what we did on the machine learning side with this library, although we had to modify several times the small summary or abstract of that library, and recently or last year in August we added something like end small convolutions, or I rephrased the whole thing. This is basically work that I've done with some colleague sitting in Intel labs in the US in Santa Clara, and then some other colleagues also in, I think he is in Portland. He's on the pathfinding future things, more a research contributor and a kind of an independent contributor. He did a lot of the work in the code generator that we have with this library. A high-level overview here is that this library is essentially a matrix or a library for small, dense, and sparse matrix multiplications and small convolutions. And in fact, there is also an API, emerging API. We just do it as a side task that covers sparse operations, real sparse things, like taking the CSR format of a particular matrix portrait, essentially, and then generating a kernel according to the portrait. And then we have supported matrix operations like sparse matrix, dense matrix, and sparse matrix vector operations and things like that. You can generate just-in-time code for such sparse or mixed operations as well. But the API for it is more, I would say, more raw and more recent additions. But we have still a good sample or host of sample code, things that got integrated, for instance, into Python, a Python framework. And we enabled some of the sparse operations there using this library. Just to say something about sparse, because it always looks like a placeholder with no life in it. General idea with this library is that general purpose code cannot be optimal. And if all cases are supported, the library is too large. We heard about upfront code generation. And in fact, some of the history of that library is that we generated upfront code using Python code, printing C code, compiling C code, and then building a big, I would say, static library containing thousands of kernels that not only had rather large compilation time because of the number of large number of kernels, but also big size, right? It was 20, 30 megabyte static library and 20 to 30,000 functions that we generated out of it. And there is a lack of specialization that hurts when matrices are 10 to 1 or 1 to 10 SIMD units on a side. And the perfect code is only needed for some cases. Then it is basically a good idea to look for just-in-time code generation. And in the beginning, or it always sounds crazy to do this because you may look at popular frameworks like LLVM. They are known for just-in-time code generation, and many people think that's the way to go. And then you look at the complexity of these frameworks, and this is not so complex in this case. It is much easier for us. So what we want to do is not generating general code just in time, but just domain-specific code. We deal only with small matrices. We deal only with small convolutions or with sparse things. And then you don't need the full variety of the x86 instruction set, not by far. We only need a handful of instructions, and if you double count, triple or quad count the flavors of, say, load instructions, of course there are a few more, but it's not a big deal. It is not a tremendous amount of instructions that you need to deal with. And in fact, we also don't do actual compilation. I will go into this detail later on. As I said earlier, we have several domains. I tried to come up with handy shortcuts for these. We have this SMM domain, we have the DNN domain that you now know what it is. We have this SPMDM, which is like sparse matrix, dense matrix multiplication. Certainly of interest in the deep learning domain as well, because you can have fully connected things and then still exploit sparsity. Something like this is of interest. And then we have more functionality on top of that is just emerging, or a proposal, and something that we have some life somewhere else to do, but we need to fill it out in later revisions. Things like a full-blown big matrix multiplication, which reuses the small matrix multiplications for tiled processing. And then we also have standalone out-of-place transpose routines, and soon to be just-in-time code generated. And then other things, we have matrix copy kernels, 2D memory regions that where we generate a copy function that can deal with copying a matrix block out of a 2D region into somewhere else. And then we have other sparse routines that fall not under SPMDM, and where I had no fantasy to come up with a shortcut yet. So the general overview here is this is focusing again on the SMM, the classic small matrix multiplication domain, but it's true in general. What we actually started with is to replace or augment BLAS, and we have at the same level we have a backend that generates static or just-in-time code for these matrix multiplications. Then we have a front end, that exposes either a compatible API with GEM compatible API, or gives you these additional functions that you looked at before, like requesting a code version or calling something like this. This front end is, I would say, specialized towards the languages so that they feel natural with the actual language, like Fortran and C or C++. So we have customization towards these three languages. And then there is also the option for applications to, of course, use the front end, but also directly use the back end. So we have code generator standalone driver programs that generate C functions. Again, they print C functions, but they contain inline assembly. And if you only deal with one certain matrix multiplication or a handful, and you don't want that library, you can just generate the code that we would generate, and then just take it and compile it with your framework separately, and that works as well. So you can directly utilize what we do in our backend to some extent. The work distribution between the authors is essentially split the same way. We have this front end, that's my work mainly. We have code generator, that's Alex Heinecke, and then we have the just-in-time JIT encoder, mainly done, or at least originally, by Greg Henry. But I believe every one of us is looking into everything, but just as an overall picture. There is more detailed things about this front end and how it works. I don't want to dig into it, but only highlight very few things that you may need in the other slides. So if you want to, if you use the GEM compatible API, you would do dispatch every time you call into GEM, because it has just the fixed signature of that function, and you have no way to express or fall back into something like this. So you would always query LIBXSMM, is there a code version? If not, it generates the JIT code and then caches it in a code registry. And it also decides when it is worth to generate such code. So you have some threshold, like this kind of formula, not the square root, but the cubic root. We want to characterize the problem size to some extent, and we updated this threshold several times. In the beginning, we had 48, 64, then we had 80 for a very long time, and recently, at some point, I just put it to 128, so that if you think about square matrices, we use our library for matrices up to 128 by 128. And even with the distorted shapes, this generalized formula for that. If it is larger, we fall back into BLAS. And also the BLAS is not induced by that library. So you can link whatever BLAS library you want and fall back to that. You can link MKL, you can link Atlas or OpenBLAS or whatever you want. It's agnostic to the BLAS that you decide about. And then there is some infrastructure behind the scenes to make the compatible API as fast as possible, to make it worth using it. And basically, we introduced a thread local code cache, which holds by default 4 instances of code versions, in flux, essentially. If you call up to 4 matrix kernels over time, you don't have to utilize the full path of querying the code version up or down to the code registry. In any case, if it is not found in the thread local cache, you would receive it from the code registry. And this is all tuned to be thread safe, as well as fast as possible, to not use any locks, right? You don't want to lock a global lock the whole code registry, then look into it and things like this. And it also deals with things like generating the code on demand, right? If the outcome of that query is there is no JIT code at this point, we just generate it, and we will look into the details on how long that would take. We already looked at this. I can just safely skip over the slide. It is just a repetition of examples that you can, it's just combined. There is no application behind it. It's just to show all of the possibilities that you have. But as I said, you have this dispatch function, which is essentially the query function that I talked about. And it would either give you the code version or it would generate it and make no further distinction between these two cases. So the primer about GEM is, of course, not needed for this audience, but the middle part actually shows you some color-coded details on the signature of the dgem or sgem function. And you can see in the beginning, we hard-coded, essentially we generated a header file from the C perspective that hard-coded whether we talk about, of course, we only supported non-transposed case. This is still true right now. And we hard-coded what kind of alpha or beta you wanted to have, and the whole library was configured to just deliver that. Then we added JIT code generation, and at some point it didn't make sense to stay with this kind of hard-coded thing. Now these yellow parts just serve as default if it is not specified. So we kept our legacy to some extent, but the blue part in general is that what is the decision we take into, or are the parameters that we take into account when we decide to generate a matrix kernel. And all these parameters impact the code version in essence. And recently we included, or what we do actually is we have a descriptor, a GEM descriptor that collects all these yellow and blue parameters into a structure. And so the structure has a certain size, this GEM descriptor. And what we do in the flow of querying a function is we do some CRC hash for the whole binary blob of that descriptor. And then we have a first stage to have some initial decision if we have some eventual hit in the code registry. And then, of course, that goes through the thread local cache, but it may end up in the code registry and just pull the code version that is there. And I already gave you some performance statistics. The whole flow down to the code, right, or sorry, to the thread local cache takes roughly, or you can call it with roughly 50 to 100 megahertz, just to find the code version. To actually, if there is no code version, to generate the code, it would take up to 100 microseconds, so 0.1 milliseconds in essence, but I have a separate slide on this. So the code registry is basically a custom data structure and algorithm for fast code retrieval. It has an arbitrary size. We still size it at compile time, but this shouldn't be a limitation, basically. We allocate basically 12 megabyte as an over allocation, as a registry, to have a good distribution out of the hash function. Although the hash is a high quality hash like CRC32, it is rock solid. So you have we minimize essentially the number of hash key collisions by having a reasonable size plus having a reasonable, I would say, hash function. And then we exploit properties like Mersenne prime numbers to simplify certain bit ops and actually achieve this kind of query speed. And there is also custom thread safety. It doesn't sound trustable because either it's thread safety or it's not, but we have certain things like atomic reads in the front, and we try to avoid locking down the code registry when we generate the code. So in effect, we have multiple locks so that we allow multiple writers on the registry at the same time, but we only enter the lock if it is really only needed. And that also leads to certain special, I would say, custom properties. Therefore, I called it custom thread safety, because if you call the code query in a threaded region with very high contention, you throw all the threads that you have on the query function and try to receive a code version, and you produce a lot of contention on the data structure. And what we do eventually is, in that case, we may duplicate some code. We may duplicate some code versions. You may generate the same actual kernel multiple times, but put it into the code registry. But this is not really a big issue or case, right? And we have also flavors to avoid these kind of things. But it gives you an idea why this is a custom data structure and what we did in order to optimize this query. Something about the code cache, but I think it's reading through. I said 4 entries only fully associative. We just search through the entire thread local cache, and it is LRU style eviction. So if you found a new or if you requested a new code version, it will override the oldest guy in the thread local storage and then deliver eventually that guy. Anyhow, what we did in the beginning, as we moved into just-in-time code generation, and that was in 2015, we evaluated different open source and Intel internal solutions for generating code, because we wanted to get around this kind of task, right? We didn't want to generate code on ourselves, so we tried to find something that does that. We looked at a lot of things, and we had a lot of ideas on what properties we wanted to have, and fast code generation, support for AVX 512. And if you look at 2015, it doesn't look so hopeful to get this, and it was actually the case. LLVM was way too slow. It is a full-blown compiler. It gives you all compilation phases. It generates an intermediate representation out of something that is eventually parsed. But of course, you don't need to parse. You call an API, generate code, and still you generate intermediate representation, do compiler phases on it, and then generate code. So it's pretty severe thing, slow to our knowledge, or what would we need. We looked at X by YAC and evaluated that. It didn't have complete AVX 512 support in that time frame. And in fact, you asked earlier on what the relationship to MKL is. MKL open sourced and adopted X by YAC as an open source framework, but later than we. So they also contributed some of the enabling on AVX 512 to fill the gaps, but they have a larger team. Of course, they could do this. And nowadays, they use this C++ framework, but the library I'm talking about is C89 on purpose. So it is C with some C++ front-end pieces, very small ones, and a Fortran front-end. So it's different flavors of, and approaches on how to get it. We also looked at XATE, some assembler from Intel. And during 2015, it wasn't open source. Although it would have saved us doing instruction encoding on our own, it was closed source, but happily enough, end of 2016, they open sourced it as well. You can find it on GitHub in the meanwhile. It is essentially something that allows you to encode instructions similar to our framework. So we decided to write our own code generator or encoder. High-level idea on how to do this is if you read this piece of pseudocode, C code here, you can see jump labels. Label 1, label 2, go to. So, and the idea is there is some code sandwiched between the two labels, and there is in fact a language extension or it's present across all C compilers, or you can easily hack it in. Even on a Microsoft compiler, you could make that work. So you can do memcopy and copy the code that is between these two labels. Surprising enough, you have this double ampersand, which takes the address of a label. The feature is called computed goto. And it copies the code. This is just a simplification. It's for fun, right? It's for your entertainment, how curious things you can do with the C compiler. And the idea, of course, is in the easiest case, you would have one instruction sandwiched between all the labels. And the initial idea was actually to visit such a label graph in order to collect all the instructions that we need along the path. It would be in reverse story, right? You jump, go to, back, go to forward. And then while you do that, you increment a pointer on the size of the instruction. And then you collect all the data or all the code that you need into some memory buffer. And hopefully you get this guy executing someone or somewhere. And reality is actually, we don't do that. We encode the instructions ourselves, easy enough. And then in the end, you have kind of a domain-specific language. The domain is called assembly programming, right? That's the way what we have. So we have an API giving you a function that is called emit load. And then the signature of that function gives you all the flavors that the load instruction has. That's the way it works. In summary, there is no intermediate representation, no automatic register allocation, no compiler optimizations, nothing. This is just writing code and encoding instructions. So it's to some extent very fast. To some other extent, you need to have someone writing that code or assembly codes like assembly programming. And that's actually, in fact, what we do. So, and there is very good potential with AVX 512 to do so because you have a very neat instruction set that is able to embed operands into the instruction itself, things you can potentially not do on a compiler side, right? If we discover that something is a constant, like a stride, you have a good chance to exploit that knowledge and make it part of the code. So for instance, small matrix multiplication with n equals 9, you can see it is all FMA, something we expected. But the interesting part is also that, so we did optimizations on KNL that folded certain address mode, legacy x86 addressing mode, like called SIB, scale index base register, or scale index base addressing mode into our code generation, and we can exploit certain things from there. And you get kind of optimal code also in terms of bubbles left in the execution pipeline for KNL. Optimal in the sense of exploiting DRAM bandwidth. Just to say this again on what the focus is on the benchmark. We have other features that are surprisingly high level. So I did all the CPU, the critical code paths are all CPU ID dispatched because this library is also upstreamed with RPM-based Linux distributions. It's lagging a little bit in the version. I think it's 1.6.1 right now. If you have the EPEL repository on Red Hat or CentOS, you can just pull the library. And so the request there is to not have any specific code. It's a little bit ancient style because nobody with an SSE only system would probably make use of this kind of library, but they still wanted to have it. The first thing they did is they removed all the compilation specific flags that we had. Now our typical baseline is SSE 4, and beyond that we dispatch everything with CPU ID, but I think the version that comes out of the RPM distribution is basically, I think, SSE 2. It's just x86 64-bit code. So there was a real need to do CPU ID dispatch. We have link time code wrapper and for static and for shared library code, so we can really replace existing dgem calls so that all dgem calls go through this library. This library looks if this code size, if this problem size is below the threshold, generates or fetches the code and calls our small special kernels. And then we have some JIT profiling. We first made use of the vTune JIT profiling API. And the good thing, and actually Google last year in August joined that project. So they are contributors, and the first contribution that they did is they added Linux perf support. So you can also profile Linux perf with the Linux perf, and essentially generate profiles and textual profiles that contain actual names for library or supposedly for our kernels. Just on the vTune side, right-hand side, you can some snapshot of the GUI. You can see a function, supposedly a function called LIBXSMM KNL DNN, and then you see the encoding MNK, LDA, LDB, LDC, and it ends up with alpha 1, beta 1, and then prefetch 6. Of course, you need the table to get an idea what prefetch strategy number 6 is about, but it is not too hard. And the thing is, this is using the API to make a name for this just-in-time generated code so that it appears as if it is a function that is called. It is a function that is called, but it has now a meaningful name. And you can see all the kernels that you actually called into. It works nicely, and it helps you to analyze. And if you click the plus, if you remind that from the vTune session, if you click the plus in front of a function, you can always see the call stack, how you ended up at this point, right? You can see all the paths that lead to these kind of function calls. Anyhow, there are developments ongoing I already talked about, like tiled matrix multiplication. I actually removed something. We focus also on Eigen C++ library, so we want to make more use of LIBXSMM in Eigen. And in fact, I think this is one field where Google may contribute or continue to contribute. So in TensorFlow, there are extensions already for Eigen library that make use of this library. In fact, they built a tiled matrix multiplication without any fallbacks that do transposes already and copy kernels already and use this library kernels. On the DNN side, we added this in 1.5. That was August last year. It was Intel Developer Forum, like a big event for us. And we wanted to have it ready there. And we refined the API in every semi-major, I would say, normally minor version 1.6, 1.7, 1.8 is kind of stable, but we will. It's based on feedback, because the largest user of that library on the machine learning side is currently TensorFlow, which aims for an integration with this library. So we just suit what we need there. That is the basic idea here. But at some point it will stabilize. And there are some features underneath of it what we actually managed to implement in order to get most of the kernels working in TensorFlow. So this is still work in progress. So every day we have to do something on that side. So we added, for instance, on the open source side, there is KNL code generation already. So we have on this open source library, we have Knight's Mill, all these new instructions that I showed before, QFMA and QVNNI, they are generated. If you had the hardware, you can just run, or if you have the SDE, the software development emulator, you can get that code path. Anyhow, I think that's it. I just updated for TensorFlow and the original intention. I think it will appear in the 1.0 timeframe, hopefully, but we probably missed 1.1 because I just realized that this is at least a release candidate since a few days or weeks. And we also have some integration, but it's more on the, it's not really an application, it's more a benchmark. We have also DeepBench hosted at GitHub. It's actually not presented here as a URL, but on GitHub you can find DeepBench, which also uses that library. And the relationship to MKL, to answer that question, because it's all what I have some references on HPC applications, and you can find some of these ones that you heard about today, like CP2K. But there are others, like Geosciences. Sisal is actually Alex's child, I would say. So CP2K is my child in that sense. Then we both had a child together, like NECbox. And then we extended that to NEC5K, the real NEC. And then Alex's child again at the bottom is this Python, the Python framework for sparse matrix operations. And that was added recently. And then we have some ML-based, machine learning-based references. Not so big yet, but main focus here is TensorFlow, not the benchmark. I think from that side, that's it. And if you have questions, I have this one question kept in mind with MKL relationship, but if you have anything else, please go ahead.
Sorry, maybe I spaced out, but you said something with reference to the eigen library?
Yes.
Could you go back and explain that again? Because I don't think it was mentioned specifically on the slide.
No, it's not mentioned specifically on the slide, so I don't need to go back because there is nothing. The thing is, when you build TensorFlow just as a make or the basal way to build TensorFlow, you have several third-party libraries underneath used by the framework, which includes LIBXSMM as an experimental path. But there is other things, I don't know if they are flagged as third-party, but there is a subdirectory created. It's not in the repository itself, called experimental, and it will contain something that is fetched right out of the mercurial repositories of eigen that then include a single header file with a tiled matrix multiplication using LIBXSMM. That is basically, they have a full-fledged matrix multiplication routine, a gem routine, which is without calling BLAS. It's their own implementation. It just uses these LIBXSMM kernels.
So that's really underneath eigen?
Yes. So, yep.
Okay, thank you.
And I think they may have added it in general, also for the regular, already packaged eigen. I'm not sure, but definitely the development version goes towards some of these things. But it could be separate from the repository. So TensorFlow pulls it. So we use it. I could actually show it, but it's too much of an effort to jump into the SSH session and show you what it pulled, but it's definitely there. I think if you type it into the browser and search for LIBXSMM eigen experimental or some flavor of these keywords, you will end up with a generated documentation page which sources this header file into it. So you could look at the actual source code if you want.
Any other questions?
Okay. So then the relationship is, in the beginning there was some, the kernels and the idea for the DNN kernels came from Intel Labs, and those have been incorporated into MKL. So you can conclude from that we have the same kernels, essentially. That's true. But then at some point, it diverged in the infrastructure, right? We used our code generator because of the legacy with small matrix multiplications, and they adopted something else. That's basically what they did. But the kernels are large extent, the main workhorses are just the same. Now it's harder for them to use or reuse our work because now we talk about features like padding, Vinograd-based matrix multiplication, transposes, and every piece has also a prerequisite, and then it doesn't fit anymore. It's not like stealing a kernel and putting it into it, and that's it. It's more complicated, so therefore it is separate. And it's also not branded. This library, you can see there's no Intel in the name, and it is not underneath of o.1.org and things like this. So we can consider this as a non-product, as a research product, or a research project, sorry. It's a research project, and then you have the products which may have an open source representation, but this is something else. It's more a research thing.
Two quick questions. One, did you say that transposes were not supported? I kind of missed that.
Yeah, so transposes are supported, but based on C code. I did rather say okayish job to do transposes. It's block-based, fixed block sizes. It's even a parallelized version out of it using OpenMP tasks and something like this. But it's not the best possible transpose code. And once I leave this workshop, I will start merging our internal transpose branch into the library, and the next version will have JITted transpose code, which is supposed to be optimal, at least from our point of view. And going from there, we can then build bigger matrix multiplication, because we now have the matrix copy kernels already. Then we will have best transposes, and then we have the matrix multiplication. All three components together, brushed up with a lot of heuristics and things like this, will sometime give us some normal big matrix multiplication.
For now, though, if we could, and they're small enough to pre-compute the transposes, would probably be...
You can just use the existing function. This is what the Google implementation does. They call our crippled, not best performing transpose routines. Perhaps they found they good enough, or they think that we improved them, and the latter is actually true. We will just keep the same interface and improve the implementation underneath of it.
All right, and one other quick question. The thing I've liked most about Eigen is probably it's kind of lazy evaluation. So sometimes we have quite complex chained expressions with, 12 to 15 different components. And I mean, when Eigen's compiling this down, I imagine it can, reshuffle these things to make things work properly. Does LIBXSMM have similar features to this, or is it basically, you work on one block at a time?
You cannot fuse multiple kernels together into something in order to optimize the call away, but this is not really an issue. It's not a bottleneck. So calling as I explained in the previous or the beginning talk today, optimizing away the function call is not a big deal. Even for the smallest matrices, this is no overhead. This is nothing. We look at this. So if they come up with lazy expression evaluation, and they get rid of some operations completely, it has nothing to do with LIBXSMM, and it's always better to not do anything if this is possible, right? And it just works. It's just orthogonal to this library.
All right, thanks.
By small, you mean matrices fitting in the cache hierarchy, mostly.
Yeah, the original idea is to focus on matrices that just fit into L2 or L1. So since L2 is larger than L1, you would safely say you have to fit two matrix shapes or two matrices into the L2 cache, because you always need two operands. And the third one is just like a scalar at the present. But yeah, that is the focus. But we are larger. In fact, what I forgot to say, if you not use the compatible dgem or gem interface, you just use the query function. You can query any code. You can ask for 10,000 by 10,000 matrices, and of course you get a suboptimal kernel, which does no unrolling. It has no cache blocking. So, but it's your your possibility to do something with that. You can dispatch on your own what you want.
My next question is, I think probably you said it, but I didn't get it. It's also parallel, the library. So if I do a call in an LIBXSMM sparse kernel, whatever, is it also parallel?
To some extent, yes. We separated multi-core parallelism into a separate library to not have the multi-core runtime in the main library. There is one called LIBXSMM-ext, which contains an OpenMP runtime. But some of the DNN, more modern interfaces, they are actually taking additional parameters like the thread ID and the maximum number of threads. So you can use any threading model on top of it and call into it. But of course, you cannot, that was your question, if you cannot expect that we parallelize a small matrix multiplication.
Yeah,
that's too small.
Because it's too small.
No,
so
it's not too small. But for the big tiled matrix multiplication, which is already present in the API, LIBXSMM-ext library, it is parallelized. It is parallelized using OpenMP threads, and then another flavor environment variable or auto detection brings you OpenMP tasking if you want.
And the final question, do you also treat symmetric matrices? At least in the extended version, which is for the larger. And
what is it? What was the terminology?
Symmetric.
Symmetric. No, so far not. No upper, lower, symmetric or things like this. Just dense, square, so far. Okay. Of course, with the sparse routines, you can optimally exploit things like this, because CSR format, you can just give a CSR description into the code generator, and you get a matrix multiplication out of it.
Yeah, the one problem with symmetric matrices is when you go parallel and
Yeah,
you
yeah.
have the dependencies
Yeah,
on,
yes,
the,
exactly.
on the
I
writing,
know.
Writing on the,
Yes.
the vector.
Exactly.
So
You have
that's why-
data races if you do a naive parallelization. Yeah, this is something future thing, a playground. You can see that I have interest on this because, but it's not there.
Okay, thank you.
Okay. Oh, one more, sorry.
So what's your recommendation if we're now developing new applications? Should we rely on this library? In what circumstances or not? So are you going to develop this and support this for a long time, or is it a research project that's going to move on?
Never know. Normally, everything starts and ends at some point. It's just from talking about experience. And where it bites you in that case would be if Intel adds a new instruction set extension that is really attractive for you, but we wouldn't implement it because it is out of our interest. That would be the worst case that you could talk about. If I think about the roadmap ahead, something you can't do, but I think we will implement upcoming things. So it's interesting to us, for us to do at least the next steps and see what it gives. So on the other hand, this is open source. You have what you have already. You can really take it home as is, and it's not going to be smaller anytime soon. You already have this feature set, right? And you can also contribute to it if you wanted to. No problem. Yep. Okay. Okay. No, there's nothing yet. Oh, so.
On the agenda, there is a question and answers.
Oh, that's true. Yes.
That's more
Sorry.
general questions.
Okay. Yeah.
I think
So that's a good reminder. Actually, that would call Michael Clem in front, and you could just perhaps then ask general questions if we want to stick with the agenda. I will just pop up the agenda, and then we will see if this is attractive to you, and then
general questions.
region into somewhere else. And then we have other sparse routines that fall not under SPMDM and where I had no fantasy to come up with a shortcut yet. So the general overview here is this is focusing again on the SMM, the classic small matrix multiplication domain, but it's true in general. What we actually started with is to replace or augment BLAS. And we have at the same level, we have a backend that generates static or just-in-time code for these matrix multiplications. Then we have a front end, that exposes either a compatible API with GEM-compatible API, or gives you these additional functions that you looked at before, like requesting a code version or calling something like this. This front end is, I would say, specialized towards the languages so that they feel natural with the actual language, like Fortran and C or C++. So we have customization towards these three languages. And then there is also the option for applications to, of course, use the front end, but also directly use the back end. So we have code generator standalone driver programs that generate C functions. Again, they print C functions, but they contain inline assembly. And if you only deal with one CI, we just do it as a side task that covers sparse operations, real sparse things, like taking the CSR format of a particular matrix portrait, essentially, and then generating a kernel according to the portrait. And then we have supported matrix operations like sparse matrix, dense matrix, and sparse matrix vector operations and things like that. You can generate just-in-time code for such sparse or mixed operations as well. But the API for it is more, I would say, more raw and more recent additions, but we have still a good sample or host of sample code, things that got integrated, for instance, into Python, a Python framework, and we enabled some of the sparse operations there using this library. Just to say something about sparse, because it always looks like a placeholder with no life in it. General idea with this library is that general purpose code cannot be optimal. And if all cases are supported, the library is too large. We heard about upfront code generation. And in fact, some of the history of that library is that we generated upfront code using Python code, printing C code, compiling C code, and then building a big, I would say, static library. So welcome back. I think it's the last session for today. Then we have lunch, and then we have these owner meetings if you want to participate in the last thing. And with this, it's actually some background to what we saw in the beginning of today with the CP2K. But what I didn't mention there was about what we did on the machine learning side with this library, although we had to modify several times the small summary or abstract of that library, and recently or last year in August we added something like end small convolutions, or I rephrased the whole thing. This is basically work that I've done with some colleague sitting in Intel labs in the US in Santa Clara, and then some other colleagues also in, I think he is in Portland. He's on the pathfinding future things, more a research contributor and a kind of independent contributor. He did a lot of the work in the code generator that we have with this library. A high-level overview here is that this library is essentially a matrix or a library for small, dense, and sparse matrix multiplications and small convolutions. And in fact, there is also an API, emerging API, containing thousands of kernels that not only had rather large compilation time because of the number of large number of kernels, but also big size, right? It was 20, 30 megabyte static library and 20 to 30,000 functions that we generated out of it. And there is a lack of specialization that hurts when matrices are 10 to 1 or 1 to 10 SIMD units on a side. And the perfect code is only needed for some cases. Then it is basically a good idea to look for just-in-time code generation. And in the beginning, or it always sounds crazy to do this because you may look at popular frameworks like LLVM. They are known for just-in-time code generation, and many people think that's the way to go. And then you look at the complexity of these frameworks, and this is not so complex in this case. It is much easier for us. So what we want to do is not generating general code just in time, but just domain-specific code. We deal only with small matrices. We deal only with small convolutions or with sparse things. And then you don't need the full variety of the x86 instruction set, not by far. We only need a handful of instructions, and if you double count, triple or quad count the flavors of, say, load instructions, of course there are a few more, but it's not a big deal. It is not a tremendous amount of instructions that you need to deal with. And in fact, we also don't do actual compilation. I will go into this detail later on. As I said earlier, we have several domains. I tried to come up with handy shortcuts for these. We have this SMM domain, we have the DNN domain that you now know what it is. We have this SPMDM, which is like sparse matrix, dense matrix multiplication. Certainly of interest in the deep learning domain as well, because you can have fully connected things and then still exploit sparsity. Something like this is of interest. And then we have more functionality on top of that is just emerging, or a proposal and something that we have some life somewhere else to do, but we need to fill it out in later revisions. Things like a full-blown big matrix multiplication, which reuses the small matrix multiplications for tiled processing. And then we also have standalone out-of-place transpose routines, and soon to be just-in-time code generated. And then other things, we have matrix copy kernels, 2D memory regions that where we generate a copy function that can deal with copying a matrix block out of a 2D